Well, today we are talking about matrices, and 7.2 is matrices. Um, Now, I love matrices. I'm so glad that we get a chance to talk about matrices here in pre-calculus right now, and that we get to finally get to these things. And it's not just because there is an amazing movie that's based off of this, well, it's not really based off of matrices, but it has the namesake and it makes a bunch of references that created huge shockwaves in the philosophical community, just revolutionizing our ideas of the nature of existence and whether or not we are actually all just in a giant computer system. The philosophers still can't disprove that as a valid theory. But matrices themselves are much. That's just the tip of the iceberg of how important and cool matrices can be. Sure, there are matrices in the matrix, but matrices themselves, if you can master matrices, you feel like Neo. Like you get these crazy angelic powers. I'm not just like trying to make a weird correlation here. Like you actually, that's I love the powers you get from matrices. You get to work with so many variables at once. It makes the people around you, their heads spin by how powerful and how many things you can do. You have all this problem solving that you can accomplish that makes people like YouTube afraid of you. You've got incredible power at your disposal, and it's not too hard. So you get this huge power, and so I'm really excited to introduce you to, well, again, one of my most favorite parts of pre-calculus is this really powerful thing called matrices. Okay, but before we get into the deep depths of what of how to do these amazing things to make their head spin, well, let me just introduce you to one of the things you can do. You may remember me bringing this little graphic up before that I wrote. There's a question that used to be a poster in my room. It says, find the solutions for all 50 variables that satisfy all 50 equations simultaneously. And when I wrote this, I don't know if I can even load the whole thing at once. But you can see this giant system of equations that I can't even load. There it is. And and here's the thing. Each one of these lines is a whole separate equation. Each equation has 50 variables in it. 50. Look at that. So that means we go from all the way from A to Z, and then after I ran out of letters up to Z, so we went through all the Hebrew letters from Aleph to Tav, and then after that I ran out of more letters, so I carefully chose two important Korean letters, I believe, and then after all of those variables, I made 50 of these, and that is a problem. And so the problem is you need to find all 50 variables that will solve all 50 equations at the same time. And that sounds impossible. Just impossible. But you can do it. And not only can you do it, not only can you do this problem, this ridiculous, insane, stupid problem, but you can do it faster than it takes most people to write the problem down. You can do amazing things with matrices, and that's what this thing is going to show you. To give you kind of perspective of what this problem is asking you, think about it this way. If you are trying to, I know I'm kind of making a tangent, but I really want you to see the power of what you have, or what you will have in a few minutes, or maybe in a few more lessons. Remember how way back in Algebra 1 we talked about how if you have two lines and they can cross each other, and if they cross each other, you can determine the exact points that they cross, and it has a one distinct point. There's an XY coordinate, where they cross, and you can do that, and that's really good. So you've got a two-dimensional plane. This is a two-dimensional plane, and you've got two one-dimensional lines. If you've got a 2D plane and two one-dimensional lines, you can find an exact point where they intersect, assuming that they actually do intersect. With a sphere, with our world, we have the same thing. You could have, in this three-dimensional world, if you had three pieces of paper, if I had three pieces of paper, and I try to make them intersect. If I made one intersect the other one, and another one, a third one, intersect these two, something like that. I can't bring them into each other. But if I could bring them into each other, make them all cross each other, then that would create. They would all cross together at one singular point, and we could determine what that point is, an x, y, z point that they all cross in. And so, what this question is asking is saying, you are in a realm that is 51 it's 50 dimensions. It's the 50th dimension. There's 50 dimensions to your world. And you now have 50 realms inside this 50th dimension that are all 49 dimensions deep. And they're just infinitely expanding in 49 dimensions. So you got 49 dimensional objects, and you're trying to figure out exactly what's the one point in this 50-dimensional realm where they all intersect. Which is, the world gets crazy after 3 dimensions. You get like squares that are pointy and spheres that are pointy and squares that are round. It gets wild. And so at 50 dimensions, it's incomprehensible. It's just, I don't know. I have no idea how to even approach that. But you can figure out the exact point in 50 dimensions, the exact point in 50 dimensions that all these 49 dimensional planes intersect in. So amazing stuff. Sorry. So I'm trying to give this really cool idea. You can do amazing, powerful things. But before we get to doing something as crazy and ridiculous as that, let's start with the basics of what we're talking about, even when we say a matrix. When we say a matrix, we're just saying a set of information. So we could say a set of information like 2, 3, 4, 7. This is a set of information. And depending on whether you're looking at the column or the row, it can mean a different thing. So you could say, on one hand, you could say how many dollars we can put it this way. If you wanted to say how many of a different pie you're selling, you could say you're selling an apple pie and a blueberry pie. And then on the top you could say, what day you're selling it. This is a weekday and weekend. And you could say, okay, so on weekdays, I end up selling 2 apple pies, and on the weekend, I end up selling 3 apple pies, and on the weekdays, I end up selling 4 blueberry pies, and on the weekend, I end up selling 7 blueberry pies. It's just a way to order information. And when you get into programming, if you would ever get into programming, this becomes almost bread and butter for a lot of the things that you'd end up doing. There are people who specialize just in this. It's called database management and putting ordered information in places and ordering a lot of information with a lot of different variables all at once. That is the specialty of those people, and they become very, very powerful people. And because they're so powerful, they also become very expensive people to hire, and they make a lot of money. But that's a different topic entirely. So how do you read a matrix like this? You'd start reading it left to right. The way I like to think about it is through snakes and ladders. I used to try to think about it like pants. I used to have a pants analogy, but it was confusing. Once because the analogy wasn't perfect, and 2 because not everyone wears men's pants. So, the apples. You want to first read left to right. So that's like a snake. So it's the snake's parts. So you read left to right, so the snakes. And then the ladders are the up and down. So you first read left to right, and then you read up and down. So you first read snakes, and then you read ladders. If that makes sense. So in other words, if we had another matrix that was 3, 5, 7, 2, 4, 6, you could say, you could try to describe this matrix and say, well, what is this matrix? What is its type? Its type is, let's see, how many rows are there? There's 1 row, there's 2 rows. So there's a 2 by, let's see, how many columns are there? I can draw 1 ladder, I can draw 2 ladders, I can draw 3 ladders. So 2 by 3 matrix. This is a 2 by 3 matrix. That's kind of what we're talking about here. Um, so that's how we read them. We read them by first reading the rows and then by the columns. It's important to realize because it can get really confusing really fast if you don't have that down. Okay, so a square matrix is that one from the first one, like 2, 3, 4, 5. This is a square matrix because it looks square. It's got, you can draw a square around it. The third one, 3, 5, 7, 2, 4, 6. This is not a square because if you were to draw a square around it, it'd be a rectangle. You have to draw a rectangle around it. You can't draw a square around it. So square matrices are square. They have the same number of rows and columns. Okay, then how about if we wanted to add and subtract two matrices from each other? Let's say you wanted to add, you had different amounts that you sold of pies for 2 different weeks. So you had 2, 3, 4, 7 1 week, and so you apple, blueberry, and you had the day and the end, the weekday and the weekend. Let's say this is a week 1, and then week 2 you sold, let's say, 3, 7, 4, and 6. You did a little bit better the next week, and so you want to figure out how many of each did I sell with both weeks. I want to add week 1 to week 2. I'm adding these two matrices together. Well, okay, you just add each element together. So on the weekdays, first week 1, I sold 2. On the weekends, on the weekdays, for week 1 I sold 2. On the weekdays for week 2, I sold 3. So I'd add those together. I got for week 1, going to week 1 plus week 2. I would just say, well, I have for weekdays with apple pies, I got 2 on the week 1, 3 in week 2, so I got a total of 5. Let's see, for weekends I got 3 on week 1, 7 in week 2, so a total of 10. So in essence, I'm just adding each coordinate, each position. So this would be 10, and then 4 and 4 would be 8, and then 6 and 7 would be 13. That's the basics of what it means to add a matrices. Same thing with subtracting. If I wanted to, for some reason, I wanted to subtract week 2 from week 1 and say how much more of each did I sell on week 1 than week 2? Well, you sold more on week 1. You sold more on week 2 and week 1. Let's say we wanted to subtract week 2 from week 1. How much more on week 2 did I sell than week 1? So week 2 minus week 1. You just subtract them. So you do 7. You do 3 minus 2 is 1. You do 7 minus 3 is 7. Is 7 minus 3 is 4. You do 4 minus 4, which is 0, and 6 minus 7, which would be negative 1. So that's the difference between week 2 and week 1. You sold more in some instances and less in that last one, in blueberry pies for the weekend. That's kind of the basics of adding and subtracting. So you can kind of relate different matrices together. Okay, multiplying matrices by number is also pretty straightforward. This might all just fall right in your intuitions as we kind of look through this. If I want to multiply this, let's say I had week 1, and I want to multiply the entire week 1's earnings by 2. Let's say we had 2 people doing this on week 1, and both of us sold the same amount. We want to figure out how much we both sold together. So we would do 2 times 2, 3, 4, 7. If I want to do 2 times this matrix, I would say, well, 2 times 3 would be 2 times 2 would be 4. 2 times 3 would be 6. 2 times 4 would be 8, and 2 times 7 would be 14. So if you multiply the matrices, you're just literally just taking the number and you're multiplying it by every single number in the matrix and making a new matrix out of that. Simple as that. That's all we're really doing there. Huh? Yeah, okay. That's all it's really taking care. That's all that's really happening. Okay. So those are the basics. Now you might be saying that's all well and good, but where does all the power come in? When do I get to do all the crazy things, and when does my brain start looking like this giant mess of numbers? Or when does our computer look like this? here's where it starts. It starts right here with this example about YouTube. Okay, so imagine this. Imagine this. You're a YouTuber, and you're trying to make it big, or you're trying to make monetization. I don't know if any of these numbers would actually be accurate in a real world scenario, so don't try to frame me or YouTube don't sue me because I don't know your numbers and your algorithms. So we have, let's say in January, we have a you're starting out and you get 1 subscriber and you get 4 likes and no shares, and in February you get 6 subs and 20 likes and 1 share, and in March you get, and so on, and you realize in April you suddenly make a video that goes viral and everyone gets crazy and your life is ruined because now you're too famous and you can never live up to that first video. But that's a whole different story. It's like winning the lottery or something. So let's say you wanted to do that, you did that, and now you want to figure out how much money you're going to make every year, or every month, and this table at the second table, let's call the first table table A, and let's call the second one table B, or matrix A and matrix B. And let's say matrix B represents the amount of money you'd make for every single for each one of these categories. Like, let's say, for example, you get 10 cents for every time someone subscribed to your channel, you got 1 cent for every time someone liked your channel, and you got 30 cents for every time someone shared your channel. And you wanted to figure out how much money you're making January, February, March, and April. So here's how you would tackle it. You would say, and rightly so, you would say, well, I've got, let's see, for January, I got one sub, and 1 sub for 10 cents. Let's see, let's not say $10, let's say 10 cents. And so it gives me 10 cents. And okay, and then for I got 4 likes at 1 cent times 1 cent, and so that gives me 4 cents. And I got let's see, 0 shares at the rate of 30 cents, and that gives me 0. It gives me 0. And I add all those together. So for January, I made a grand total of a whopping 14 cents. And so you would do that and you say, okay, so for January I got 14 cents, and you do the same process for February, and the same process for March, and the same process for April, just taking ages and ages to do this, and it would take you forever. And that's the long way of doing it. But if you know matrices, and you know how to use calculators that can use matrices, you can do it all instantaneously. Because this is the way that a matrix works. What you're doing right here is you're doing matrix multiplication. You're taking the values from one, matching them with the values of another, and multiplying them together and adding them up. That's exactly what matrix multiplication is. It seems really complicated when you think of it as just a bunch of letters, numbers, but really all we're doing is just we're matching things up, we're multiplying them, and then we're adding up our answers. Okay, so here's how this would look out in numbers. So we would end up at the very end. We'd end up with a little table of the amount we made for January, February, March, and April. Jan, Feb, March, and April. Okay. And you'd have 4 prices. The first one would be 14 cents, and the rest of them would be some other price. Okay. And so this is what matrix multiplication is. So let's say for example, and let's just kind of define what we did here and what makes sense and what doesn't make sense. If we said A, let's say, what is A? A is let's see, we got 3 rows, so that's a 3, and we got 4 columns, so it's a 3 by 4 matrix. Yes, 3 by 4 matrix, and yes, and we have a matrix B is a, let's see, we got 1 row and 3 columns. There's a 1 by 3 matrix. So what we're doing here is essentially we're taking B, we're taking the money, and we're applying it. We're applying the money that we're making, or the money table, to the actual subs and likes and shares we've got. We're applying the money table to the money, the likes, and the shares. Or yes, to the likes, the subs, likes, and the shares. We're applying the money to the months. And so that's kind of what's going on here. Here's something that wouldn't make sense, right? So if I said if I said we got subs, likes, and shares, and then you got some extra amount for you got views, and you want to try to multiply this in, well, the views doesn't really matter. It's kind of irrelevant because actually I don't know. I don't know how much money I'd make for a view. I could make 1 cent. I could make a third of a cent. I could make $20. I don't know. I don't know how much money I make for views. And so if I started adding the number of views I have in a situation, I would get something I couldn't multiply and couldn't work through. So we would see here that a 4x4 matrix wouldn't multiply with a 1x3 matrix. And that doesn't work out. Similarly, if I went down this way, and I said we've got, let's move this to the right just a little bit. All right, that'll have to do. Actually, no, it won't do. Let's do this right. Let's say I'm gonna. Oh no, I'm gonna erase that because I made a problem. Okay, let's say I added a little bit extra on here, and I said I put views here, and I said a view was worth 1 cent, for example. Now that would create another problem too, because now I can't multiply. I can't fully apply the money scheme to the time to this table of January, February, March, April. And so I can't just be adding variables on like this. So that wouldn't work. So here let's just kind of formulate what this means. If I've got a 1x3 matrix, I've got a 1x3 matrix, and I'm trying to multiply that by a 3x4 matrix. These threes have to be the same number. They always have to be the same number. Because if I had an extra number, or have one less number, if I have an extra view category in either one, or if I'm missing a category in either one, they don't line up, and I can't really combine them well. So these have to be equal. In other words, B, if you have AB, if matrix B was A by B, and matrix A was C by D, then multiplying those together, then B must equal C. I have to be the same. That's what we're trying to say here. That's the official formula of it. But the idea is that we can't add extra categories on to multiply, because that doesn't make much sense. Okay. So yes, when we actually do the multiplication, let's see what we're actually doing here. We actually multiply this out. We've got a 3x1 matrix, 1x3 matrix, and we're multiplying it by a 3x4 matrix. Okay. So 1, 2, 3, 4. So here's what we're doing. When we multiply these two things together, you can notice we first multiply the 10 cents by the 1 cent. Well, actually, before we even do this, let's kind of, how do I represent 10 cents well? How do I represent this little cell well? Well, I can say this. I can say this is 10 cents. This is the column. This is the matrix B. And let's see. It is row 1, column 1. I can say that's row 1, column 1. So I can put a little notation here and say that's matrix B, row 1, column 1. That way I can always, instead of trying to say that 10 cents, I can always give a unique identifier to identify it with. So I can be kind of clear with what I'm talking about here. I could say the second one is row 1, column 2. And the third one's row 1, column 3. So it's not B11, B12, B13. It's B11, B12, B13. Over here we can do the same thing. We can do, for the first one, we could say we have, for the subs for January, we can say that's A11. And then we can say the likes for January, that'd be A21, row 2, column 1, and then A31, row 3, column 1. Remember, we do rows first, so the snakes first, and then the ladders, the columns next. And then we just go on. So A12, A13, A14. And so if I want to identify, say, this last one, this one would be it'd be row 3, column 4. Okay, so that's kind of the notation we're kind of making for these things. All right, so when it comes to this, once we've done this, we can kind of think about mashing all of this together, we can say we've got row 1. If I want to do this correctly, I'll take B11, and I wish I had more space for this. I need to, can I move this out of the way? I don't know if I can move it out of the way. I can't move it out of the way. No, I'm good. I don't think I can. Oh, I can. There we go. Oh, never mind. It's not gonna work. Oh well. I tried. And now I'm making it worse. Okay, let's get out of this. So let's say I wanted to multiply these two things together. I would start by multiplying the subs of the price for subs by the subs of January 1. So I would start by saying subs of B11, the price for one sub, and multiply that by the price of the first one, A11. So B11 times A11, then I'll do B, let's see, I would do B11 too, a second time. I would take that same thing and multiply that by, let's see, the likes for January 1. So A21. And let's see, I would do the same thing. I would take B11 and multiply that. No, sorry, I wouldn't take B11. I'd take B12. Take B12. I'll take the likes, the price for likes, and multiply that by the number of likes I got. And then I'll take the price for shares and multiply that by the number of shares, A31. And then I would add all those together. That's kind of what we're doing here. So we'd multiply the first, we'd multiply, if I want to figure this out, I would add all these three things together, and I would get my full total price for that first of 4 categories. Okay, that first of 4. Now it seems for the January money. Okay, so here's what I'm kind of doing then. I said I've got one row. I've got this first row here, this row for money, and I'm going to multiply that row for money by every single column. And so I'm going to multiply this row, this one row, by all 4 columns. So for the first row, in the first column, I'm essentially, if I want to multiply these two things together, I'm multiplying row 1 of B by column 1 of A. And then for the second one, I'll do the same thing. I would take, I'm in row 1 of B, and I would multiply that by column 2 of A. Here's what's interesting about this. I can keep saying, well, if I want to take this one row, I want to multiply by every single column. I want to take this sub count, I want to multiply by this by this by this, and I'm going to do the same thing for March, and the same thing for April. So I'm going to do this 4 times, and so for each time, I'm taking this one row, and multiply every single column. So now I've got 4 columns and 1 row, and the coordinate of each point tells me which row and which column I'm multiplying by with. So you can say I've got 1 row, and I'm multiplying that 1 row. This would be row 1, and I've got 1 row that signify this 1 row up here. Maybe it's a little bit confusing. Let me try to give you a different example to help make this even clearer. Let's say I took a different multiplication. Say I had a different set of things I'm multiplying together. Let's suppose it was something like this. I wanted to multiply a 2 by 2 matrix with another 2 by 2 matrix, and we had 3, 4, 2, 7. We're multiplying that by 1, 2, or let's say 1, 2, 6, and 5. Okay, I want to multiply these two matrices together, and so the resulting matrix, as a rule of thumb, remember, if we multiply these two together, these middle two have to be the same, and they are the same. The resulting matrix will conveniently be the outside. It'll be a 2 by 2. If this was a 3 by 2, if this was a 3 by 2 over here, and this over here was a 3 by, I don't know, let's say it was a 3 by 4, the resulting matrix would be a 3 by 4 matrix. but it's not. So it's just a 2 by 2. So we'll say it's a 2 by 2 matrix. 2 by 2. And so we'll make another 2 by 2 matrix. And so where is this? What's going to be in this first one? So this first one will be row 1. These are our rows and column 2. When it comes to multiplication, you really only need to separate the first one into rows, the second one into columns. Because remember, we do rows, then columns. And so we'll take the row of the first one. Let's call this matrix C. This is C1, 1. To do C1, 1, we've got to multiply row 1 with column 1. Because it's row 1. This is the point 1, 1. So we'll do 3 times 1 plus 4 times 6. 3 times 1 plus 4 times 6. For C1, 2, this is not C1, 2. This is row 2, column 1. We will multiply the second row by the first column. Second row, first column. So we would do C2 would be 2 times 1 plus 6 times 7, and so on. And we keep going. So C2, 1 and C2, 2. We would take the second row. We would take the second. Yeah, we take this. No, this is not. This is C1, 2. First row, second column. We would take the first row and multiply that by the second column. So 3 times 2 plus 4 times 5. And at the bottom, we'd have the second row, second column. So 2 times 6 plus 7 times 5. And so it goes, and so it goes. That's the way to multiply matrices. You can get a new matrix that makes sense. Okay, this can get really confusing, really daunting, really fast. So that's why I'm trying to go really slowly to help you understand it. Feel free to back up and rewind and try to really make sure you get this point down, because this is really, really important and it can be tough. If you need more help on this, just let me know. I'm here to help walk you through that bit there. Okay, so you do that, and that is multiplying matrices. How about if you want to divide matrices? The problem with dividing matrices is that there's no easy way to do division. We can't really just say one matrix divided by another matrix. So it's really almost impossible to do. What we can do, though, is do a rule that we kind of heard before, back in arithmetic, to kind of cheat our way through it anyway. So let's say you wanted to divide. Let's say you want to divide 16 divided by 8. Well, let's say you couldn't do division, and you couldn't actually do division. You wanted to do something else to give you the same answer. Well, you could say instead of saying dividing by 8, what I can do is I can multiply 16 by the inverse of 8, or 1 over 8, and that'll give me 2. This will give me 2. If I multiply by the inverse, 1/8, which is like 0.125, I will get 2. And so that's what we're trying to do here with matrices. We don't really have a good way of doing division as division, but we can make inverses. And if we can make inverses, then we can multiply by inverses to kind of do division. Okay, well, how to do an inverse? What is an inverse, first of all? What is the inverse of a matrix? Well, the inverse of a number, if you have a number 8, the inverse of 8 is 1/8. What's the relationship of 8 and 1/8? Well, if I multiply 8 with 1/8, I get 1. If I had any other number, say 16, if I find the inverse of 16, the inverse of 16 is 1 over 16. If I multiply 16 by 1 over 16, that gives me 1 as well. So the really relationship between a number and its inverse, or even a matrix and its inverse, is they both multiply to be 1. A matrix times its inverse is 1. We call this inverse. We say the inverse if you have a matrix, its inverse is a to the power of -1. Just in the same way, if I took 8 and took 8 to the power of -1, that equals 1 over 8. That is what 8 to the power of -1 is. So the inverse of a matrix is the same thing. That's kind of what we're trying to do here. So this is probably this is where you get really, really powerful, but this is where things can get really confusing if you're not careful. So here's the whole point of doing division with matrices. Well, why would you want to do this in the first place? Well, it helps you kind of get around places you're not supposed to get around and do things you're not always supposed to be able to do. You can discover things that seem almost impossible. Like, for example, if you're a YouTuber and you're watching YouTubers and a YouTuber reveals their salary, how much money they're making, and then you find the the number of likes and shares and comments and views and all those things together. If you can find that, and you can find that for a few different YouTubers, their salary and how much money they're making with each of these things, or no, it's not uh, how much they're getting those likes, comments, shares, and views. You can multiply. You can make an inverse matrix and divide in order to get their exact get the actual value and the exact worth that YouTube ascribes to a like, a comment, a share, and a view. You could figure out what this is. Oops, I erased that. You can figure out how much a like, a comment, a share, and a sub is actually worth. Of course, I don't know this because I just don't. But you can think about how powerful that would be if you knew just exactly how much each like, comment, share, and sub was valued for. You would know how to make people money. You could make bots that did exactly what they needed to do to get likes or get shares or get comments in a particular YouTuber, so that they could make as much money as they could ever want. So this is incredibly important. This is why a lot of YouTubers skirt around and don't try to really try heavily not to answer how much money they make. And it's probably why YouTube probably restricts them from telling you how much money they make, because they know if you are a pre-calculus student and you figure out matrices, you can use inverse matrices to figure out exactly how much each of these things is worth, and therefore figure out how to break the system. And that is what we don't want. We could do a lot of really illegal things by figuring this out. So let's figure out how to do illegal things so we don't do them. So this is the nature of inverse matrices, and this is probably one of the hardest parts of matrices, is just understanding inverses, because it can get really weird. And so I'm not going to go into all the specifics and details because we don't need to get too deep into that. It gets really heady really fast. But let's say we have a matrix, a simple matrix like a 2 by 2 matrix. It's got A, B, C, and D as its 4 places. It could be 1, 2, 3, 4. It could be whatever you want it to be. And if we want to find the inverse of that matrix, here's the formula for finding it. We would do 1 divided by AD minus BC, or we're going to multiply that by DA, or D negative B negative CA. So here's what this would look like if I did this 1, 2, 3, 4 matrix. We do 1 divided by, let's see, A is 1 times D is 4 minus B is 2 times C, which is 3, 2 times 3, and we'd multiply that answer by, let's see, it'd be 4, let's see, negative B would be negative 2, and then negative C would be negative 3, and A would be 1. There's a really good reason why this actually works the way it does. I don't have too much time to really get into all the details. Again, it gets really heady really fast. But just for now, just take my word for it. So this would become, let's see, 1 over 1 times 4 times negative 2 times 3. This would be, let's see, 1 over 4 times 4 minus 6. This would be negative 1/2, negative 1 over 2 is what that would be on the left side. And if you multiply that by 4, negative 2, negative 3, 1, you get, this becomes 2, negative 1, negative 3/2, and, or no, so not, this multiply by 1/2. It'd become negative 2, 1, 3/2, and then negative 1/2. And so that would be the inverse matrix. This is the inverse matrix of 1, 2, 3, 4. And so if I was to multiply these two matrices together, I would get 1, or something called the identity matrix. There is a matrix you can multiply by that'll make everything exactly the same. that will keep things exactly the way they are. Here's what that identity matrix is. If I multiplied A by the identity matrix, I will get A. That's the kind of idea that we're trying to work with here. So what is the identity matrix? Let me just put this over here. The identity matrix, identity, is in a normal number just 1. If it's a 1 by 1 matrix, it's going to be just 1. If you want to expand the square a bit to make a larger identity matrix, we can make it 1 1 0 0. It'd be kind of like a diagonal of ones. If I was to make it even bigger, if I was to make it like a 3 by 3, we would get 1 1 1, and then everything else would be zeros. So you can see there's a diagonal of ones in there. And I encourage you, go ahead and try multiplying this matrix by anything, or anything by this matrix more accurately. And you'll see, if you multiply an appropriate sized identity matrix with anything else, you will get that exact same matrix out. You always come out, because this is the x value, this is the y value, this is the z value, this is the 1 2 3. So it only allows one of the x's, one of the y's, and one of the z's. It's kind of a very sterile computation. And again, I think just going through it and actually doing it myself would be more confusing than helpful. I think if you did it yourself, you'd find it very, very maybe insightful. Maybe it'll click for you if you try to multiply yourself. So I encourage you to do so. Okay, but assuming you did, or assuming you don't care enough to try, or that doesn't matter. I mean, if you don't want to try it, I don't really care. That's totally fine. It's totally fine. If A is one thing you want to notice, if this denominator down here became 0 because of multiplication and subtraction, if that somehow ended up becoming 0, then you couldn't solve this problem, because you'd get this. If that was 0, you'd have 1 over 0 times something. And you know 1 over 0 is undefined. If we try to multiply anything by an undefined number, it'd be impossible. We could not solve it. It'd be unsolvable. And so that's the case with this. That's the case with this. If AD minus BC ever equals 0, you know you can stop immediately and say, no, there is no inverse to this matrix. Some matrices, like that one, would not have an inverse. So just be aware of that that's the case. So I mean, if you want to try one example, the matrix 1 1 1 1. If you try to do that, that would give you 1 over 1 times 1 minus 1 times 1. That would give you 1 over 0, and that would give you problems. And so there is no inverse to the 1 1 1 1 matrix. It doesn't exist because we just can't solve the problem. So that idea, this AD minus BC, we call this little bit here that if it ever becomes 0, it'd be undefined. We call that a discriminant. That is called the discriminant. Not discriminant. I guess some places called discriminant. It's also called, probably more accurately called the determinant. It's a good thing that I have these notes in front of me. This is called the determinant. Okay. So we have this determinant, but other matrices have this determinant as well. So for example, if you went to a 3 by 3 matrix, things get really messy and really confusing really fast. And I don't want you to go through to figure out how to do an inverse of a 3 by 3 matrix, because that's just way too much work. But I would like to make sure you're aware of the determinants and how to find the determinant. So if you've got a 3 by 3 matrix such as this one, you can find the determinant by following this process. You take A21 and multiply that by A11, A33 minus A13 and A32. And then you do the same thing with A22. You take A22, you add that to A22, multiplied by A11, A33, and then A13, A31. Oh, excuse me, I did the first one. This is to be A13, A32. There we go. That seems a little bit more accurate. Yeah. And then finally, if you were to do A23, you do A23, that'd be A11, A32, yeah, A32, and then A12, A331. Very good reason as to why this is. But again, for the sake of your time, I don't want to overly confuse you with what's going on here. So I'll just give this to you as a formula. This is the way that works. If you want miscellaneous notes, if you wanted to, again, that's a density matrix. That's what it looks like. It's just a diagonal of ones. If you want to find a to the t power, what's that saying is it's transposing the A matrix. So if you have a matrix 1, 2, 3, 4, 5, 6, the rows become the columns and the columns become the rows. This is row 1 and this is row 2. This is column 1, column 2, column 3. And so row 1 becomes at the top, row 2 comes at the top, and then we have column 1, column 2, column 3. You kind of transpose it. Very, very helpful if you've got a lot of information and I use this all the time. I use the transpose function all the time in Excel because when you have a lot of information and I want to say quickly move it all from one category as on the left and one category is on the top. I want to change it quickly so that category is now on the top category is on the left and the left category is on the top, but I want it to be the same data. And so this is what does that. It gives you the same data, but it just switches the two variables. Okay, so that's all that's basically all you need to know from the rest. We're just going to walk through the problems. A lot of the problems are maybe a little simpler than what we just talked about, but we're going to kind of just mosey our way through and see what we can do to try to get these done. The first one says, determine the order of the matrix. Indicate whether the matrix is square. Well, you would say the order of the matrix, let's see, we've got 2 rows, 2 snakes, and 3 columns. We do snakes first, then ladders. So we have 2 snakes, 3 ladders. So we have 2 by 3. Is the matrix square? Well, no, that's a rectangle. This is a rectangle. That would not be a square. So this is no, because the number of rows and columns are they're not equal. They just don't equal each other. So that's the answer number 1. Number 2 says determine the order of the matrix, indicate whether it's square or not. Well, we've got 1 row and we've got 2 columns. So we've got a 1 by 2 matrix. Is it a square matrix? Well, no. Again, this is a rectangle. This is not a matrix. This is a rectangle. So that would also not be a square matrix. This would not be a square matrix because they have to be the same number of rows and columns. If we added 2 more, if we added say like 3, 4, now that would be a square matrix. But this is not the case. This is not the case, so it's not a square matrix. Okay, what is A12 for the matrix? So we say this is A12. Again, it goes row, column, snake, ladder. Row 1, column 2. So we'll say this row 1, column 2. Row 1, column 2, because it's 10. So 10 is our answer. All right. Simple as that. Pretty straightforward stuff overall so far, I would think. Next one says, find the following matrices where A equals A7 with that, and the matrix B equals this matrix over here. Let's see. The first thing it asks us to do is to find A plus B. Okay, so that means we take each entry and match them up. So we say row 1, row 2, column 1, column 2. We'll take this entry and match it with that entry. 8 plus 1 is 9. And let's see, we'll take 7 plus 1 is 8. Let's say 2 plus 2 is 4. And then 5 plus 7 is 12. And so that is our matrix. Okay, so that'd be A. Now, let's see. B, A minus B. Okay, 8 minus 1 is 7. Let's see. 7 minus 1 is 6. Let's see. 2 minus 2 would be 0. And let's see. 5 minus 7, that would be a negative 2. So our matrix would be 7, 0, 6, negative 2. Okay. Now let's see this next one. It says negative 5 times A. Okay. So that'd be let's see, we just take each entry and we multiply it by -5, and that's our answer. We're taking each one and multiplying by -5. So we get 8 times -5 would be -40. Let's see, 7 times -5 would be -35. And 2 times -5 would be -10. And then 5 times -5 would be -25. And that would be that answer. So I just multiplied, I took each one and I multiplied it by -5, and that's all it is. Okay, this last one is a little bit dicier. It's just an extra 2 steps. So we do 4a plus 3b. We can still follow order of operations in this. You know, the whole how we do multiplication first, then addition. So let's do the multiplying first and then add the results together. So let's see, we first want to find 4a. Let's clear this up a little bit. So 4a, that would be, let's see, 4 times a would be 32, 28, 8, and 20. And then 3b, that would be 3, 3, 6, 21. We add those two together, and so we get, let's see, that should be 35, 31, and then 14, and 41. That is our matrix. So I'll write that up here. 35, 31, 14, 41. And that is our answer. Cool. And that's it. That's all we have to do for 3. So again, this is a lot more, for now, things are pretty straightforward. And I think I hope this isn't fully confusing yet. Again, if you understand the row and column thing, the first bits can be not too overwhelming. Okay. Number 5. Find the following matrices where A is that matrix and B is that matrix. Same process. So we'll do A plus B, and we get, let's see, we'll do A plus B, it'd be -6 times 5. They're just larger matrices. Instead of being a 2 by, I think it's, it's 2 by 2, we have a 3 by 2. This is a 3 by 2, and this is a 3 by 2. So we're just adding those together. We'll just take each entry at the same location and put them together. So this becomes -1. This becomes -8. This becomes -4, -6 becomes -10, and then -7, -9 would become -16, and 6 and 6 would become 12. 7, 0 would become 7. So let me see. Yeah, -1, -8, -10, -16, 12, 7, and there we go. Great. And then for the next one, let's see, A minus B. Let's see. So -6 minus 5 would be -11. Yes. And then -5 minus -3, that'd be -5 plus 3, or -2. And then we have, let's see, -4 minus -6, that's -4 plus 6. So it becomes 2. Then -7 minus a -9 would be -7 plus 9, which is 2. And then 6 minus 6 would be 0. 7 minus 0 would be 7. And that's it. So those are our answers for there. 3a. We take each entry and multiply it by 3. Be -18, -15, let's see, -12, -21, and then 18, 3 times 7 is 21. And that's all we have to do there. And finally, D, 3a plus 8b. This would become, let's find 3a and 8b first. So 3a equals, let's see, it would be -18, -15, -12, -20, -21, -18, and 20, no, that's a positive 18, and 21. Okay. That's right, that 15 better, so it's not confusing. That's still confusing, but you know what? We'll have to go with it. This is a -21. Okay. And then 8b equals, this becomes 8 times 5 is 40, and then -24, and then -48, and negative 72. And then we have, let's see, 48 and 0. We add those two together, and that's what goes down at the bottom. So let's see, negative 18 plus 40, that would be 22. Then we have negative 15 plus 24, that'd be, sorry, negative 15 plus a negative 24, that'd be a negative 39. Negative 39. And then we have negative 12 plus negative 48, that'd be negative 60. Negative 60. Then negative 21 plus a negative 72 should be negative 93. Yeah, negative 93. Large numbers, but they are accurate. 18 and 48 would add to be 66. And then the last one I think is easy because it's 0. It's 21 plus 0, so that's just 21. So that is our answer. There it is. Okay, number 6. Find the, we're going to do the same thing again. More of the same, more of the same. Okay, A equals 193 and B equals negative 7, 7, and 6. Okay, A plus B, A minus B. This is a 3 by 1, and this is a 3 by 1. 3 rows, 1 column. 3 rows, 1 column. Okay, A plus B. We can do this. A plus B, 1 plus negative 7 would be negative 6. Let's see, 9 plus 7 would be 16. And then 3 plus 6 would be 9. And that's all there is to that. Then, let's see. A minus B would be 1 minus negative 7. So that'd be 8. Then we have 9 minus 7, which is 2. And 3 minus 6, which would be negative 3. Negative 3. Okay. And then negative 2a, we can do that. That's negative 2, negative 18, and negative 6. Okay, and then finally 4a plus 3b. So 4a, let's say 4a equals, let's do that down here so the space. So it would be 4 and then 36 and then 12. And then b would be, let's see, it'd be 3b, is that right? Yes, 3b equals negative 21, and then 21, and then 18. We add those two together, and we get 4 plus negative 21 would be negative 17, and then 36 plus 21 would be 57. And finally, let's see, 12 plus 18 should be 40. Yeah. No, it's not 40, 30, excuse me. Negative 17, 57, 30. And that's our answer. Okay. Alright, number 7. This is where things can get really tricky, and we've got to be really careful, not because this is particularly difficult in many different ways, but it's mostly just that it's really easy to make a mistake. So let's really crank down on this and make sure we do this exactly right. Okay, so it says, find, if possible, A times B and B times A. It gives us a matrix A and a matrix B. Here's what you want to do. First, rewrite A and B so it's easier to see. You want to say negative 9, negative 3, 1, 9 for A. And for B, you'll have negative 7, 6, negative 3, 4. Because you're doing A times B. That's what we're doing here. Okay, now here's the condition. Make sure, we're wrong already. It's negative 3, negative 4. Make sure immediately you check your work and make sure you wrote down these numbers correctly. Because if you wrote down any number incorrectly, you'll have it all wrong. Or at least it's very easy for me to write down these numbers incorrectly. So don't do that. Make sure you check your work. Then from here, remember we always do rows, then columns. So divide A up into 2 rows and B up into 2 columns. Divide them by columns. So you'll notice this is a 2 by 2 for A and a multiplying that by a 2 by 2 for B. You'll notice that the insides, because the inside numbers, the 2 and the 2, are the same number, we can multiply them together. If they were not the same number, we could not multiply them together. The outer two numbers will tell us, those tell us specifically how big the matrix will result in. So we have a 2 by 2 answer. Our answer will be 2 by 2. Okay, so how do we actually do this though? What is the process? Well, we can take row 1 and row 2. We'll label them row 1 and row 2, and column 1 and column 2. The process is we take every single row and we multiply it by every single column, and that'll give you all of the entries in rows and columns. So for example, we'll start with row 1, and we'll multiply that by column 1. To do that, we'll multiply each entry by each entry. So we'll do negative 9 times negative 7, and then we'll add that to negative 3 times negative 3. And that will be, we did row 1 and column 1, so that'll be entry 1 in our matrix. Entry 1. Okay? Now if we were to do the next one, let's say we were to do row 1 times column 2. We would do negative 9, take the first entry times the first entry, so negative 9 times 6, and we'll add that to the second entry times the second entry, negative 3 times negative 4. Let's get rid of that. Oh no, negative 3, oh, let's hope it doesn't break, negative 3 times negative 4, oh wow. Okay, then let's see, that's row 1 times column 1, and row 1 times column 2, so that was row 1, column 1, and we did row 1 times column 2. Now let's do row 2 times column 1. Row 2 times column 1 would be 1 times negative 7. Again, I'm just doing every single possible combination I can make. And then 9 times negative 3 plus 9 times negative 3. And then row 1 times column 2. Sorry, not row 2 times column 2. 1 times 6. And then we're add that 9 times negative 4. And then once you work all these out, those will be our answers. So we'll get 9 times negative 7, that is 63, plus 9, which is 72. And then negative 9 times 6 is 54, negative 54. And then negative 2 times negative 4 is 12. 54 plus 12 is 40, negative 42. Okay. Then we'll do 1 times negative 7 is negative 7. 9 times negative 3 is negative 27. Those added together would be negative 34. And then finally we have 1 times 6 is 6. 9 times negative 4 is negative 36. Those added together, that gives us 40, not negative 4, that gives us 42, that gives us negative 30. Negative 30. So it's very easy to make a mistake. So do your best to really check your work and make sure you're doing everything correctly. If it's helpful, you may just want to focus on row 1, column 1, and finish all row 1, column 1 first, and then row 1, column 2, and then row 2, column 1, and just do one entry at a time, and see and make sure you're doing it thoroughly every step of the way. But that gives us our answer to be negative 2, sorry, 72, negative 42, and then let's see, negative 34, and I think the last one's 30, negative 30. And that is our answer. I don't know how they ask you to enter them into the system. I think it's some, hopefully, I imagine something pretty straightforward though. If you have questions, let me know and I can help walk you through it. I'll figure it out and help you. So that's that. The second one is B times A. And again, make sure you're writing them down carefully so you're not making mistakes. But we'll write B first and then A second. So we'll do negative 7, 6, negative 3, negative 4. And those are our first sets. And we'll multiply that by, this is B times A. And A is negative 9, negative 3, 1, and 9. And so that is a 2 by 2 times a 2 by 2. Because the 2's in the center are the same, this does work. We can multiply them together. And the resulting matrix will end up being a 2 by 2. 2 by 2 will be our resulting matrix. So let's go ahead and multiply them through. So we end up with, let's see, negative 7 times a negative 9. let's see, let's do row 1. Let's see, we got row 1, row 2, column 1, column 2. We've got row 1, row 2, column 1, column 2. We're kind of just combining them together. So row 1 times column 1, that'd be -7 times -9, that'd be 63. 63 plus, let's see, 6 times 1 would be 6, so that'd be 69. 69. And then -7 times negative, so for row 1, column 2, we'll do -7 times -3, that's 21. 6 times 9 is 54, so it gives us a total of 75 is what we should have, yep. And then we have, let's see, row 2, column 1, which is -3 times -3 times -9, which is 27. We'll add that -4 times 1, which is -4, so that gives us a total of 23. And then finally we have row 2 times column 2. That'd be -3 times -3, be 9. -4 times 9 is -36. So that gives us a total of -27. And that's our answer there. So our final answer is 69, 75, and then 23, -27. 23, -27. And that is our answer. Great. So now we're going to get something a little bit, slightly different. This one, for this problem specifically, we're going to multiply let's see, this is a 3 by 2 matrix against what is this, 2 rows, 3 columns. A 2 by 3 matrix, and see how that pairs up. So let's see, we've got A times B. We'll do the same thing. So we'll do the rows, row 1, this is row 1, row 2. This is column 1, no, hold on, excuse me. We'll do the rows first. So we'll make rows, row 1, row 2, row 3. And the second one will be columns. So we'll divide this into columns. So column 1, column 2, column 3. So A times B will be, we'll start off by multiplying you can see by looking at the end, this become a 3 by 3 matrix. But by looking at these ends, this is a 3 by 3 matrix. And we can multiply them together because the 2's in center are the same. However, this will look, if you don't remember it's going to be a 3 by 3 matrix, you can just start multiplying them together and see what you get. Row 1 times column 1, that'll give us our first entry. Row 1 and column 1, that gives us 1 times 3, which is 3, plus -1 times 0, plus 0, so that gives us a 3. Then for the second one, we'll multiply row 1, column 2. So that means we'll have on the first row, we'll have a second column. So this would be -3 times 1, -3, -1 times -3. This would be plus 3. So the second column would become 0. And then row 1, column 3. Row 1, column 3 would be -1 times 0, which is 0. -1 times -3, which is 3. 0 plus 3 is 3. And then we're going to go to the second one. -1 times -1 times 3. So row 2, column 1 be -1 times 3 would be -3. And then -4 times 0 would be 0. So it would be -3. And then -1 times -3 would be 3. -4 times -3 would be 12. Yes. And then so we get 15. It's 15. -1 times 0 is 0. -4 times -3 is 12. It's 12, so that gives us 12. Okay, that's the second one. Let's see, we take row 3, multiply that by column 1 to start off with row 3, column 1 of our matrix. So we get 5 times -1 is 15. -1 times 0 is 0, so we get 15. And then on the bottom, and then we have, let's see, 5 times -3 is -15. -1 times -3 is plus a 3, so we get -12. We have 5 times 0, which is 0, plus a 3, that's a 3. 5 times 0 is 0. -1 times -3 is 3, so that gives us a 3. And so our final matrix is 3, 0, 3, negative 3, 15, 12, and then 15, negative 12, 3. That is our final answer. Okay, and then we would have, yeah, so then after that we would do B, which is the inverse. We do the well, not the inverse, the opposite. We'll replace B with A. So we'll do this. Negative 3, we'll do 3, 3, negative 3, 0, 0, negative 3, 3 on the left, and that's split up into 2 rows, row 1 and row 2, and then we'll have the 2 columns. 1, negative 1, negative 1, negative 4, and then 5, negative 1. So that gives us 2 columns. So column 1, column 2. So 3, negative 3, 0. That gives us, let's see, we start off by multiplying the first row with the first column to get our first entry. So we get 3 times negative 3 times 0 is, well, actually before we do that, just to make sure that, just to show you that they do multiply, this is 2 rows times 3 columns, and 3 rows times 2 columns. These two 3's are the same, so we can multiply them together. They can work. They can work together. Okay, so 3 times 1 is 3. Negative 3 times negative 1 is 3 plus 3, and then 0 times 5 is 0. So we get 6 for the first entry. Then row 1 times column 2, we get 3 times negative 1, which is negative 3. We get negative 3 times negative 4, which is 12. And we get 0 times negative 1, which is 0. All those added together, that gives us 9. That gives us a 9. And let's see, let's see the second column. 0 times negative 1, or sorry, second row, excuse me. Second row, first column would be 0 times negative 3 times 0 times 1 would be 0. Negative 3 times negative 1 would be 3. And then 3 times 5 would be 15. All those added together would be 18. And then 0 times negative 1 would be 0. Negative 3 times negative 4 would be 12. And 3 times negative 1 would be negative 4. So it gives us 8. Okay, so our final matrix is 6, 9. Let's see, so hold on, I'm make sure I did this right. 0 times negative 1 would be 0. Negative 3 to 12. Oh, this would be, yeah, it'd be negative 4. Yeah, so it would be negative 3 times negative 1 would be negative 3. Negative 3. Yeah. Okay, so that would give me, yeah, if I did that right. Did I put these numbers in correctly? Oh, this is a negative 3. All this time is a negative 3. Oops. Let's fix that. So this would be, excuse me, I wrote the numbers in wrong. This would be a negative 15. Negative 15, and this would be a positive 3, which would change these answers a little bit to be negative 12 and 15. If you're following along, got the wrong answer, and you got a different answer to me, that's why. That's I put in the wrong numbers. Okay, it's really easy. It is really easy to make a very simple mistake in these problems. So it's important to be vigilant and continually check your work, because when I was going through this the first time, I made mistakes left and right, not because I didn't know what I was doing, but just because I just made careless mistakes like I just made there. So let's be careful together. Okay. Number 9. Find, if possible, A times B and B times A if if one matrix equals, if A equals this and B equals that. Okay, let's see. Let's try this. This is row 1, row 2, row 3, and then column 1, column 2, column 3. Okay, just like so. Okay, so 1 times, let's start with row 1, column 1, and that gives us, let's see, 1, and then negative 8, and then 4, and then we have, for that first one, which gives us, let's see, it'd be negative 7, and negative, negative 3. Yeah, negative 3 for the first one. And then we have row 1, column 2. We've got 1, we got 5, we've got 5, 0, and negative 8, which gives us negative 3. And then finally we've got 1, negative 2, yeah, no, we got 1, we've got 3, 3, and negative 8, and then 0, which gives us negative 5. Yes. And then for the second row, we're multiplying it by that first column. So that gives us 1, and then negative 8, and then 0, which gives us negative 7. And then for the second one, we've got 5, row 1 times column 2, sorry, row 2 times column 2. That gives us 5, and then 0, and then negative, it's 0 times that is 0, so it gives us 5. And then finally we do row 2 times column 3. So that gives us 3 times a negative 3 and a negative 8 and a 0. So it gives us negative 5 for our second row. Row 3 times column 1. Let's see, we get 0, it should be easy, 0, 0, and negative 5. So that's negative 5. We get 0, 0, and negative, we get 0, 0, and 10. So we get 10. And then we get 0, 0, and 0, so 0. Okay, so altogether, our final answer is negative 3, and then negative 3 is at negative 5, and we get negative 7, 5, and negative 5, negative 7, and then we get negative 5, 10, and 0. That is the first one. Secondly, and I think it'd be due for a break after this one, is we have b times a. Yeah, we're definitely due for a break after this one. b times a. We'll do the same thing, except we're just going to reverse them. So 1, 4, 1, 5, 0, 2, 3, 4, 0, and then 1, negative 2, 4, 1, negative 2, 0, 0, 0, 5. Okay, and we'll split the b into rows and a into columns. Okay, we'll multiply those together. So 1, 5, and 3. So the first one is 1 times 1 is 1, 5 times 1 is 5, 3 times 0 is 0, so it gives us 6. And then 1 times negative 2 is negative 2, 5 times negative 2 is negative 10, and then 3 times 0 is 0, so that gives us negative 12. And then finally we have 1 times 4 is 4, 5 times 0 is 0, 3 times 5 is 15, so 19. Is that, no, I didn't, I made a mistake somewhere here. Did I put these numbers incorrect? I put this as a negative 5, so that'd be negative 15, which gives me, I would have screwed my whole column there if I didn't notice that. 15 times, or negative 15 and 4 makes negative 11. That's okay. Is that right? That looks right. Yeah, I think that is right. Good. Okay. So second row then. 4, 0, 4. So we have 4 times 1 is 4, 0 times anything is 0, and then 4 times 0 is 0. So our first one is 4. Then we have 4 times negative 2 is 8, 0 times anything is 0, 4 times 0 is 0, so that gives us negative 8. Then we have 4 times 4 is 16, 0 times anything is 0, and then 4 times negative 5 is negative 20, so that gives us negative 4. And then we put, so that's our second row. That looks about right. Then our third row is 1 times 8 is 8. 2 times 1 is 2. 0 times 0 is 0, so that gives us 10. Then we have 1 times negative 2 is negative 2. We have 2 times negative 2 is negative 4. 0 times 0 is 0, so we get negative 6. And then we have, let's see, 1 time, oh, hold on, this is a negative 2 here. So I want to make sure, I made a mistake again. I'm still getting this wrong. So let me try this again. Let me try this again. So 0, 1 times 8 is 8, negative 2 times 1 is negative 2, and then finally 0 times 0 is 0. Let's make sure that I'm not, let's see, 8 plus a negative 2 should be a negative 6. Let's see, I'm still, when I do this, when I have this, the answer from before, it's still looking a bit odd here. Let's see, what am I doing wrong? I got 1, negative 2, 0, and then 1, 1, 0. I think this is right. 1, negative 2, 0, and then let's see, row 1, 1. Oh, obviously, I'm multiplying this all wrong. Let me try one more time. Third time's a charm. 1 times 1 is 1. Negative 2 times 1 is negative 2. And 0 times 0 is 0. So that gives us a negative 1. Okay, good. Now, 1 times negative 2 is negative 2. Negative 2 times negative 2 is 4. And then 0 times anything is 0. So we have just positive 2. It's a positive 2. And finally, 1 times 4 is 4. Negative 2 times 0 is 0. And then 0 times 5 is 0. So we have 4. So our final answer, after all of that, is negative 6. Negative 6, 6, negative 12, negative 11. 6, negative 12, negative 11. Then we have 4, negative 8, negative 4. And finally, we have 1, negative 2, 4. Is it negative 1? Negative 1, 2, 4. Don't beat yourself up if you make small minor mistakes. Everyone makes mistakes when they're doing matrices by hand like this. It happens. Because it's you can see how many computations it is. And unless you've grown up in an elementary, and in elementary they drilled into you mathematics to the point where it was bleeding out of your ears, it's easy to make mistakes. It's easy to just kind of not really get it down, or your brain have to think fully at one point and just do a minor miscomputation here and there. That can mess a whole lot up. You can see I did it a couple times. But let's take a break and then move on to number 10. Alright, so find A times B and B times A, or state the product is not defined. Again, we got a pretty interesting combination here. Let's quickly just do this. This one shouldn't take too long at all, considering the way it's set up. Let's go ahead and do it. So we've got a 1 by 3 matrix and a 3 by 1 matrix. Okay, A is, let's see, A is 5, negative 2, 4, and 5, negative 2, 4, that's row 1, and then negative 2, 2, 2, that is a column 1. So we have one entry in this, and you can see that because 1 times 3 and 2 times 1, the 3's line up, which means we can combine them, and the 1's tell us what the answer is. The answer will be a 1 by 1 matrix. Okay, so let's see, we'll do first entry times first entry. We'll do negative 2 times 5 is negative 10, negative 2 times 2 is negative 4, and plus negative 4, and then 4 times 2 is plus 8, so it gives us a total of negative 14 plus 8, which is negative 6, so it should be negative 6. So our answer for this one is just negative 6, just the set of a 1 by 1, negative 6, and that's it. Alright, how about this next one? How about the other way around? This one gets us a dramatically different answer, as you might notice really soon here. Let's see, so we write it the other way, negative 2, 2, 2, and we get 5, negative 2, 4. So we've got row 1, row 2, row 3, and then column 1, column 2, column 3. And we've got to do each one for each one. Okay, this is a 1 by 3. No, this is a 3 by 1. There's a 3 rows in one column, 3 by 1 by a 1 by 3. So the 1's match, which means we can combine them. And the 3 by 3 tells us we're going to end up with a 3 by 3 matrix. And we'll see in just a second why. So let's see, row 1, column 1. Negative 2 times 5 is negative 10. Let's see, row 1 times column 2, negative 2 times negative 2 is 4. Row 1 times column 3, negative 2 times 4 is negative 8. Let's see, row 2 times column 1, negative 2, 2 times 5 is 10. Row 2 times column 2, negative 2 times 2 times negative 2 is negative 4. And then 2 times 4 for row 2 column 3 is 8. And then finally, so 2 again. So we'll get 10, 2 times 5 is 10, 2 times negative 2 is negative 4, and then 2 times 4 is 8. So our answer is that right there, that big, that rather large, relative to the other two matrices, rather large answer. So negative 10, 4, negative 8, 10, 4, 8, or 10, negative 4, 8, 10, negative 4, 8. That's our answer. Okay. Find the matrix product if it's possible. So we have A times B and B times A. Let's see. We'll start with A times B. We've got a, what is this? This is a 1 row and 3 columns, and we got 3 rows and 3 columns. You might notice here that things aren't the same as they were before. Things are a little bit different. So let's go ahead and write this up. So negative 1, 7, 1. That is row 1. And then we have, let's see, our columns. Column 1 is 6, 3, 0. Column 2 is negative 1, 1, negative 1. And column 3 is 2, 0, 4. Now because these 3's line up, we can do it, we can solve it, and our result will be a 1 by 3 matrix, 1 row, 3 columns. Okay, so let's start with row 1. Row 1 times column 1. That'll give us row 1 times column 1 is negative 6 plus negative 3, which is negative 9, and then plus 1 times 0, plus 0 is negative 9. Then row 1 times column 2, that'll give us our second entry. So row 1, and then column 1, column 2. Row 1 times column 2, which would be negative 1 times negative 1 is 1. 7 times 1 is 7. And then 1 times negative 1 is negative 1. So that gives us a total of 7. Yeah. And then we have, oh, did I do the first one right? Hold on just a second. I'm checking my work here. So 7 times, yes. So row 1 times column 1. This would be 21. Sorry about that. If you were confused, I understand why. 21 plus 0. So this would be a total of 15. There we go. Very easy to make mistakes. Again, very, very easy to make mistakes. Let's see, there we go. That's column 2. Column 3 is negative 1 times negative 2. Negative 1 times 2 is negative 2. 7 times 0 is 0. And 1 times 4 is 4. So that gives us a total of 2. And that looks about right. Yes, okay. So we have 15, 7, and 2 is our answer. 15, 7, 2. Those commas I put in are kind of optional. You can put them in. You don't have to put them in. But if you are working in a database, oftentimes databases use commas to separate different values. There's actually a whole file type called CSV, which stands for comma separated values. Every number or every value, whatever you put in there, is just separated by commas to represent the new ones. So you can put in the commas in there or not. I think that the actual, your program, you're on that website is going to ask for no commas, probably. So letter B, B times A. Let's set this up. So we got 6, negative 1, 2, 3, 1, 0, 0, negative 1, 4, and we got negative 1, 7, 1. So we got row 1, row 2, row 3. We've got column 1, column 2, column 3. And so we're left with a 3 by 3 matrix, and we're going to multiply that by a 1 by 3 matrix. Now you'll notice in this one, we have a 3 and a 1 in the middle, which shows us we cannot multiply these together. We cannot combine them. Not this way anyway, not in this order. And you can kind of see why. If you start trying to do this, you'd run into a lot of problems. I mean, you could try if you want to, but then you get row 1 times column 1. You get 6 times 1 is negative 6 times negative 1 is negative 6, and they get negative 1 times what? Negative 1 times, there's nothing to multiply negative 1 by. There's nothing to multiply 2 by. We have no entries to multiply them by. So we're just at a loss of what to do. We can't solve this problem. So this one cannot be multiplied together. It's not defined. So we'll just put B, not defined. The 3 and the 1 do not combine. The 3 and the 1 are not the same number. The insides are not the same. Okay. Number 12. This one's a rather straightforward one. Once you know what to do, you'll be like, oh, this is no problem. It says determine the values of x and y that make the matrix equation true. Well, it's saying this one matrix equals this other matrix. They're the same matrix. So we're saying this, if these are the exact same matrix, then this value is the same as this value. Then this value is the same as this value. They're the same matrix. Which means if you just look at it visually, you'll say, well, okay, well, what is x? X, if you look to the right, x is just negative 1. And 1 is the y. That's all there is. And that's really all there is to it with these. I don't think they will require you. I mean, I suppose you could try to multiply. No, I think this is all they're going to ask you to do. I think this is as straightforward as it gets. They're not going to, I don't believe they'll ask you to multiply this side by 2 to get something more rational, more understandable, to get like 2x over and 2 for your entries. I think it's just going to be, I think that's it. Cool. 13. Determine whether B is the inverse of A. This one's a little more complicated. So remember, when we're getting inverses, things get strange really, really fast and get really, really heady really fast. And I tried not to give you too much at once for this. Let's go back and remind ourselves of how to do the inverse of a 2 by 2 matrix. Way up at the top, we have this right here. We have this. Oh no! Oh, I don't know if I can select it. Oh, if I have selection on, maybe that would help. Oh, okay. But you see, it's 1 over AD minus BC times D negative B negative CA as our pieces. So let's go ahead and copy that. I'm going to paste that back down here once I find 13 again. Okay. We've done a lot of work already. Okay, we're going to paste this in just so we have it for reference. Would that work? Or maybe not. I want to paste right to the side. There we go. There we go. Okay. Let's say, okay, so we've got, is B the inverse of A? Let's find the inverse of A and then see if it is B. So A is 2, negative 5, negative 1, 3. 2, negative 5, negative 1, 3. That's what that is. And let's see, that is matrix A equals A, B, C, D. Okay? Because we read it left to right, rows and columns. Okay. So let's figure this out. Be 1 over, let's see, AD, so it'd be 2 times, let's see, 3 minus, let's see, B times C. So it'd be negative 5 times, minus negative 5 times negative 1. Okay. Now, if this ends up being 0 on the front end, we know we can't solve this because we'll get something undefined. Remember, AD minus BC, this right here, this is our determinant that tells us whether or not we can it determines whether or not we can actually do this. Okay, so let's just quickly solve that one real fast. So this would be 1 over 6 minus 5, so it'd be 1 over 1. Well, that's convenient. We'll do 1 times whatever this matrix is. So we get 1 over 1 times, we get 1 times, if it wasn't too sloppy there. Let me just rewrite this so it's not a little less sloppy. I hope it's not wasting your time. Okay. 1 over 6 minus 5, 1 over 1, which is 1. So 1 times this matrix. This matrix is, let's see, A. Let's see, we start with D on the first one. So D is 3. And then negative B. So we will make that a 5. Negative C. So C used to be negative 1. We'll make it a positive 1. And then A. A used to be 2. So 2 is over here. So 1 times 3, 5, 1, 2. 1, that means take 3, 5, 1, 2 and multiply all those, each number each position by 1. So we just get 3 times 1, 5 times 1, 1 times 1, and 2 times 1, or just 3, 5, 1, 2. So is that B? Is that B? 3, 5, 1, 2? Yeah, 3, 5, 1, 2. That is. So we have the inverse of A. Great. 14. Find the inverse of the matrix if it has one, or state the inverse does not exist. Same deal. All right. So we got 1 over, let's see, let's make sure we have that right. AD minus BC. AD minus BC times, let's see, that was D negative B negative C A. Okay. Let's go ahead and solve this. Remember, this is A, B, C, D. So we've got 1 over, let's see, A times D would be negative 12 times, or negative 12 minus B times C, so it'd be negative 5. 1 times negative 5 is negative 5. And we're going to multiply that by all the matrix. Let's see, 3, negative 4. You kind of swap the diagonals, and then take the other diagonal and make them both negative. Negative 1, 5. Okay. And then we will take, we'll work with this. So we get negative 12 minus a negative 5. That gives us 1 over negative 7, or negative 1/7, times all of this. 3, negative 1, 5, negative 4. So you multiply that through, and you get 3 over 7, negative 3/7. Then we get, let's see, 1/7, and then negative 5/7, and then 4/7. And that is our answer. Yep. So we get 3 over 7. Let me see if I can write this small enough. 3 over 7, negative 1 over 7, negative 1 over 7, 5 over 7, and then negative 4 over 7. And, oh, no, negative 3 over 7, positive 1. There we go. That's what it was. Is that right? Yeah, that's right. Okay. And so that would be the inverse. Okay. Find the inverse, or state that does not exist. Let's start by finding that discriminant. Remember, the discriminant of the inverse of this is of a 3 by 3 is much different from a 2 by 2. And every single time you get to a larger square that you try to find the inverse of, it gets more and more complicated. So I've just only given you these two. Let's start by finding this discriminant. Or sorry, not this. I keep saying discriminant. I mean determinants. Can I get the whole thing? There I can. There we go. I'm going to copy that. Then I'll bring that down. Copy that. Roger. Okay. Through 15. Yep. So we'll go down here and we'll paste that in. All right. The determinant is 1, 4. Okay. So we'll just let's label these. Well, maybe you don't have to label them. We can kind of get the idea of what's going on here. We have 1, 4, negative 2. 1, 4, negative 2. 3, 2, 1. And finally, 4, 6, negative 1. Okay, let's go ahead and work this out. So the determinant is 2, 1, coordinate 2, 1. So that would be the row 2, column 1. That'd be negative 3 times row 1, column 2. Row 1, column 2. So that'd be 4. And then times row 3, column 3. That'd be negative 1. 4 times negative 1. Let's keep the parentheses correct. Minus 3 times, minus row 1, column 3. So that'd be negative 2. Negative 2 times row 3, column 2, which would be 6. So let's see, that'll be, just to reduce that down real quick before we go into the next one, that's 3 times negative 4, and then negative 2 times 6 would be negative 12, but it's changed to a positive 12 because the minus sign. So it gives us negative 4 plus 12 is negative let's see, that'd be 8, and then negative 24. Okay, so negative 24 plus, let's see, row 2, column 2, that is 2, and we'll multiply that by row 1, column 1, which is 1. Is that not? Yes, not negative, that's just 1, times row 3, column 3, which is negative 1, plus, no, not plus, a minus, excuse me, minus, negative 1, minus row 1, column 3. Row 1, column 3 is negative 2. And then row 3, column 1, which is 4 times 4. So that becomes, this becomes, let's see, this is negative 1. And then negative 2 times 4 is negative 8. But with the minus sign, it makes it a positive 8. So that gives us 2 times a positive 7. So it'd be 14, plus 14. Okay, 2 times positive 7 is 14. Yeah, I think that's all right. And then minus row 2, column 3. Row 2, column 3. There we go. That is 1. And that's 1. It is 1, right? Just to make sure. That is a 1. Okay, 1. And then times. Oh, actually, is that not a parentheses? I want to make sure I'm doing this really carefully so I'm not making mistakes, because it's really easy to make mistakes. Row 1, column 1. That is a 1. You know that. And then row 3, column 2. That is a 6. Times 6 minus row 1, column 2, which is a 4, times row 3, column 1. That is a 4. Yeah, that's also a 4. 1, 2, and 3, 1. Yep. Okay, so this becomes a minus 16. Yes. Yes, it becomes a minus 16. Just checking my other work because that sounded familiar. And then 1 times 6 is 6. So 6 minus 16 would be minus 10. So minus 10, but then there's a minus over sign over here, so that makes it, all this together becomes a plus 10. Okay, so we've got negative 24 plus 14, so that'd be a negative 10, and then yeah, and then negative 10 plus 10. So this become negative 10. Negative 10 plus 10, that equals 0. Oh, well, good. It's a good thing we did this discriminant thing, because now that we found the discriminant, we realize, without even having to go through the giant formula, the determinant is 0. There is no inverse to this. So we can immediately stop here and say there is no inverse. The matrix does not, because if the determinant is 0, you're dividing by 0 at some point, and you don't want to do that, ever. Just make sure my mic's on real fast. Oh man, I made enough mistakes today. Alright, 16. Now again, we're going to find the determinant of the matrix, which is the same, basically the same thing as we did just before. We're just going to do the exact same thing. Now again, let's be really, really careful. Take your time and go slowly, because I just did this problem a second ago and I got it wrong, so this is a second take. Because that's not because I did the wrong computation, it's just because I wrote down the problem wrong, because I was trying to be really fast, so I wouldn't waste time. But no, we gotta take the time and we gotta do it right. So 4, 0, 2. My big problem is that I'll write 2 negative numbers, and the first one will be a negative, and the second one will be a positive, even though I meant for them both to be negatives. I'm learning. I'm doing that all the time. Okay, let's see if we can figure out this one well. Let's see. So we just gotta find the determinant, and the determinant is this formula right above here. So we'll take negative row 2, column 1. Row 2, column 1 is a 4. We're going to multiply that by row 1, column 2, which is row 1, column 2 is a 3. And then row 3, column 3 is a 2. We're going to subtract from that row 1, column 3, which is a 2. And row 3, column 2, which is a 0. If you can't go as fast as I can in your problems, don't worry. It just comes with time. So negative 4 times 6 minus 0, which is times 6, would be negative 24 is our first number. Then A22, not A22, row 2, column 2 is the center one. It's a negative 4. And then we have row 1, column 1, a 3, and then row 3, column 3, which is a 2, minus row 1, column 3, which is a 2, and then row 3, column 1, which is a 4. Okay, so 2 times 4, this gives us 6, and then minus 8, which is 6 minus 8 is negative 2. Negative 2 times negative 4 is 8. So plus 8, and then we're going to do the last one, which is minus row 2, column 3. Row 2, column 3 is a negative 2, minus a negative 2. Is that right? Yeah, minus a negative 2. And then times row 1, column 1, which is a 3, times row 3, column 2, which is a 0, times 0. And then minus row 1, column 2 is a 3. And then row 3, column 1 is a 4. Make sure that you're doing this correctly and you wrote down your numbers right and you're doing your math carefully, because I would hate for you to get the wrong answer and then have to do the whole thing over again just to figure out what you did wrong. So yeah, just make sure you go slowly. This is 12, and then we got 3 times 0 is 0, so 0 minus 12 is a negative 12. Negative 12 times negative 2 is a positive 24, so that becomes a positive 24, but there's a minus sign, so we get minus that positive 24. So we get a negative 24 plus a negative 24, which is a negative 48, plus 8, which is negative 40. And that is our answer. So let's go ahead and plug it in. The determinant is negative 40. Great. And that's all there is to it. Okay. So number 17. Number 17. It says solve for x where a equals 5, 6 and b equals 11, 3. Let's go ahead and do that. Let's plug this in just so we can get a kind of idea of what's going on here, because this can look a lot more daunting than it is. It's much simpler than you might think. So we'll take this. This is 2x plus 5, 6, 5, 6, and equals 11, not 11 over 3, it's just 11, 3. The matrix 11, 3. And okay, so we'll do, to solve this, we'll need to get x all by itself is really what we're going for, just like any algebra problem. We can do this by subtracting 5, 6 from both sides. Officially, we can't subtract 5, 6 from both sides. It's not like that works now. This is not that kind of algebra problem. But what we can do is we can add the negative version of each of it from both sides. Negative 5, negative 6, and we can add that to it, and we can add on this side negative 5, negative 6, which is essentially the same thing. We're basically doing the exact same thing as adding. So subtracting. So if you want to think about it, you're subtracting, just go ahead and subtract 5, 6 from both sides. That works too. So these 5, 6 cancel out. They become an empty set, becomes 0, 0. An empty set is nothing. We can actually get rid of an empty set. Empty set doesn't matter anymore. Unless it's being multiplied by something. If it's being multiplied, it's like 0 times something. An empty set is kind of like a 0. You can just, it doesn't exist, or it does exist, whether you want it to. It's like 0. So we're left with 2x equals 11 plus a negative 5. We're adding these two matrices together. This negative matrix and matrix B. So 11 plus negative 5 would be negative, not negative, that'd be 11 minus 5 would be 6. And then 3 minus 6 would be a negative 3. Okay, great. So finally, to finish this up, we can divide both sides by 2. But again, we can't really divide by 2. It's not really allowed per se. But what we can do is multiply by the inverse, or as we often have called before, multiply by the reciprocal. We can multiply by the inverse. So we can multiply 1/2 times 2, and then this times 1/2. Or maybe more helpfully, this is actually what we're really doing. We're doing 1/2 times that. So the 1/2 times 2, they cancel out. So we're left with x equals 6 times 1/2 is 3. And then negative 3 times 1/2 is negative 3 halves. So 3 negative 3 halves is our answer. 3 negative 3 halves. That matrix is our answer. Let's try to make sure I'm going to do this clear as possible. There we go. Is it 2 separate numbers? And that's it. That's all we have to do. So again, nothing really crazy with discriminants and inverses and all this other stuff. I can get to that, but this one is fortunately pretty convenient in that regard. Okay. Happy Valley Farms. Ah, great. An application question, but this actually becomes useful for some reason, for some purpose. Because these are really, really applicable and very, very useful things. We have Happy Valley Farms produces 3 types of eggs. 1 large, 2 extra large, and 3 jumbo. The number of dozens of type I eggs sold to grocery store J is represented by Aij in matrix A, shown to the right. The price per dozen that Happy Valley Farms charges for egg type I is represented by I1 in matrix B, shown to the right. Okay, complete parts A and B below. Okay, let's first try to digest what this is even saying, because there's a lot of really mathematical mumbo jumbo here. Let's just kind of think this through. They've got 3 types of eggs, type 1, type 2, type 3, and the number of dozens of type I eggs sold at the grocery store J is represented by Aij. So Aij in matrix A. So it's talking about matrix A. For matrix A, we're saying that I, the first one, is the number of eggs. And we say Aij. So I is your row number, J is the column number. So our row number is I eggs. So our rows are eggs. So egg 1. So I guess large, and then row 2 is extra large, and then row 3 is jumbo. I wonder why there's no like medium or small or normal sized eggs. They're always large whenever I go to the grocery store. I never thought about that. I wonder what happens to all the mediums, or maybe none of them are medium and small, and they just kind of market it that way as large, extra large, and jumbo. I don't know. So they gotta have some use for small eggs. Anyway, okay, that's aside. That's not relevant. Okay, so that is shown to the right. What does it say the J is? J is the grocery store represented. So let's say it's grocery store 1. Let's call it grocery 1 and grocery 2. So the 2 grocery stores. I'm gonna go ahead and erase this down here, this over here, because this is kind of in our way, and I'll make our green partition. There we go. And then let's see. It says matrix B. It says egg type I is represented by I1, I column 1. So egg price is, so this is still large. This is large because that's column 1, and then extra large or 2 is column is row 2. So yeah, large is row 1 because that's I, and then extra large is row 2, and then jumbo is row 3, and column 1. Says column 1 is the price. Okay, and so that's matrix B. That's how matrix B is laid out. Okay, great. So here's what it's asking us to do. It's saying find the product of the transposition of B, or B transposed, times A. Okay, this is a little difficult. Well, not too difficult. It's actually not. I mean, if you've been handling everything else so far, this is nothing. So this is. Let's see. We're gonna first transpose B, and if you remember from way back in the beginning of the lesson, we said that transposition means that we're gonna take all the rows and make them columns, and all the columns and make them rows. Just kind of switch things up a bit, so we can have the same information but represented in a more usable way. So we'll say that B transposed is the dollar amount, and we have 70 cents, we have 85 cents, and we have $1.10. And we have, let's see, that's large, extra large, and jumbo. That's 1, 2, and 3 type eggs. Okay, so we need to find the product of the transposition of B times A. So we're going to multiply that times A. Okay, so this is a row 1, column 3 times matrix. We're going to multiply that by 100, 60, 130, 80, 250, 130. Okay, and that is a row, 3 rows and 2 columns matrix. 250, 130. Great. Okay, so we'll go ahead and multiply this through. Let's see, we're going to do, this is one row, these are the columns. And we'll do, let's see, we'll start with row, because it's a 1 and a 2, we'll end up with a 1 row and 2 column answer. So 1 row and 2 column. So it'd be something like that as our answer. And let's see here. Let's see. Oh yeah, this is grocery store 1. This is grocery store 2. This is large, extra large, and jumbo. Okay, let's go ahead and put these together. So let's see. Let's 100 times 70.7 is 0.7. Let's go ahead and I'm just gonna go ahead and use a calculator so I don't waste your time. 100 times 0.7 is 0. Is 70. Is 70. And so 70, and then or $70. And then we have 70 cents times 130. 70. Let's do 0.7 times 30, or 0.7 times 130. That is 91 plus $91. And then finally we have let's see, $1.10. Did I do this right? No, I didn't do this right. No, I'm not doing this correctly. So we do 70 cents times $1. That's that. Then for the second one, we do row 2. We do the second entry in the first row times the second entry in the first column. So that'd be 85.85 times 130. I wonder if you caught that before I did. So that's 110.50. And then finally, we'll do entry 3 times 250. That gives us $275. That really made a killing. Plus $275. And so that plus 110.50 plus 70 all equals 455.50. 455.50. So that's our first entry in our matrix. Okay, and then our second entry will be, let's see, we'll do the same thing. We'll multiply the different types of eggs times the different grocery stores. Times grocery store 2 times column 2. So 70 cents times 60. 0.7 times 60. Pretty simple, is 42. So $42. And then 85 cents times 80. 0.85 times 80 is $68. $68. And then 110 times 130. Let me make sure I'm writing that correctly. Yeah, 130 times 130 is 143. So plus 143, and that gives us plus 68 plus 42, and that gives us 253 total. Okay, great. Okay, so it's 253 total. Make sure I'm not doing that terribly. Yeah, that makes sense. If you sell fewer eggs, you're as grocery store 2 definitely did, you're gonna make a lower income. So what's going on here? What's this? So actually, let's start with this. The answer to the first one is 455.50. 55.5. I think that this is supposed to be dollar signs, but and cents, but the program is probably going to ask you just to put it in a decimal. So just put it in a decimal, not the dollar sign too. So this is 455.5, no comma. You don't need a comma for the program, and then a 250. Is that right? 250, 253. So 253. So 1 row, 2 columns. That's what we end up with. Okay, that is the product of those two things. Now it asks us, what does it actually mean? What does it represent? Well, here's what's going on. We just took the prices of each egg, and we multiplied it by the number of eggs we stole. We stole and sold at each grocery store. So we figured out how much we earned for the large eggs by multiplying the number we sold by 70 cents. We figured out how much we earned from the extra large by 85 times the number of eggs, and the jumbo by 110 times the number of eggs. And so we added all three of those together. So if we add all three of those entries together, all those three of those products together, those prices, those sorry, not prices, the incomes from each different types of eggs in a grocery store, well, we'll get all of the income from a grocery store for that egg, for their eggs in total, for all of their eggs in total. So so the first entry would be all of the total income from eggs from grocery store 1, and the second entry would be all the eggs of income from grocery store 2. Or another way to think about it, we notice that this is that the first one is a 1 by 3 matrix, and the second one is a 3 by 2 matrix. The 1 by 3 comes from this dollar sign. Well, the one, it's one row because there's one price, there's $1 sign. The 2, the 1 comes from the dollar sign. The 2 comes from the 2 grocery stores. There's 2 different grocery stores involved. And so when oh, hello Neo. When we get the answer of 2 grocery, oh my, sorry. When we get the answer of 2 of a row one row and 2 columns. Yeah. Oh my, what is happening? Yeah, if we get an answer that's 1 row and 2 columns, this answer is 1 row by 2 columns. And the 1 row, we know that because we're multiplying this together, we think something is 1 row and 2 columns. The first row is a dollar sign. The 2 columns are grocery store 1 and grocery store 2. So it tells us the money from grocery store 1 and the money from grocery store 2. So that's kind of a way to help interpret what's going on. You can take those n bits and put them together in that sort of way, and that can kind of help you figure that out. Okay, so let's see, what are the options here? We got the matrix. The matrix represents the number of each type of egg purchased per dollar. We've got that's not the number of each egg purchased per dollar. We didn't purchase. No, it's the number of amount of total income per egg, or for all the eggs sold per grocery store. It represents the price for each type of egg. No, it doesn't. We already had the price for each type of egg. That was the B matrix. The total cost for the farm for each type of egg. Well, it's not like no, there's only one farm, so we only know there's only one farm. We're just giving us the total income for each grocery store. It says represents the total cost for each grocery store. I guess you could say cost for each grocery store. I mean, I guess it's income for the grocery store. I suppose. Oh, I guess they were sold to grocery stores. So they were sold to grocery stores. So I guess that was the price for the grocery store to buy them. I thought it was the amount that the grocery store was making off the eggs. But I suppose it's the amount they bought, the amount they paid to get those eggs from the farm. So I guess that makes B the best answer. It's the total. I was thinking the total income for each grocery store, but it looks like it's the total cost for each grocery store. Okay, great. That's number 18. Number 19. Prove that the image of a point under a reflection across the y-axis can be obtained by matrix multiplication. What is that talking about? Sounds like we need to bring out a graph. So let's get some graph paper going here. Let's see. We need to prove that the image of a point under a reflection across the y-axis can be obtained by matrix multiplication. Okay, so we've got. This is a tough one. We've got. Let's go ahead and start by making axes to help us orient ourselves. Let's say we've got a point. So let's say this is the points x, y, because that's what those points are. And we say, let's say that the image of a point under a reflection across the y-axis. I'm pretty sure that just means the point after you reflect it across the y-axis, the reflection of the point down here. So let's say if we reflect it across, across the y-axis, it'd be the point over here. Right? Yeah, the point over here. The image of the points under reflection across the right. Yeah, you reflect across the y-axis. That's what the point is. So x negative y. That'd be where we are. So the same x, no, not the same x negative y. It's a different x, it's negative x, and then the same y, same height, but opposite side of the y-axis, so negative x. Okay, so that's our point. And it says, prove that we can get that through matrix multiplication. That's what we need to do. Okay, so this is going to be a tough one. This is a point in the Cartesian coordinate plane can be represented in a 1 by 2 matrix xy. Okay, so we're saying this is our matrix A. We got xy. If the point xy is reflected across the y-axis, its matrix form after reflection is, oh, well, we just figured that out. That's negative xy. The point afterwards is negative xy. So we'll say it's the matrix negative xy. That's our rows and columns. Okay, let's see. Since the point's original matrix form and its reflected matrix form have one row and two columns, that makes sense. This is a 1 by 2 and a 1 by 2. Let's say this is matrix B. These are both 1 by 2 matrices, 1 row, 2 columns. Then a matrix A such that xy A is equal to the reflected form would have to have. Oh, hold on. They're not saying that's matrix A. They're introducing a new A. Never mind. So they're saying then a matrix A such that xy times A, so the multiplying these two matrices together, is equal to the reflected form. We'd have to have so many rows and so many columns. Okay, so we want to end up where they're saying let's call this, I don't know, let's call it matrix M, just so that we know they're not going to come up with anything else. So we're saying M times A equals, we want to get that to matrix, that first matrix times A, it's got to equal this this matrix here. It's called R. So matrix R. Okay, R. I should have come with something more clever like man or ma or something. I don't know. Anyway, so it's saying that these two matrices together would create that matrix, and we need to figure out what makes that second matrix. You know that second matrix needs to be a 1 by 2 matrix, and we're given a 1 by 2 matrix, and we're going to multiply it by some other matrix to get a 1 by 2 matrix. Okay, so we're multiplying a 1 by 2 times some matrix. We need to end up with a 1 by 2. Well, in order to actually do the multiplication at all, we need to have the first set to be a 2. We need to have a 2 so they actually can multiply. And then the other end, we have, let's see, this and this are the result of this and whatever this is. Well, we want a 2 at the end, so we'll have to say that is a 2. So that means our matrix, our A matrix, has to be a 2 by 2 matrix. So it has to be 2 rows and 2 columns. That's the kind of matrix we're looking for. All right. So to get the matrix form of the point after it's reflected, multiply xy by the matrix something. Okay. So we need to multiply it by something. But we need to figure out what that actual matrix is. Okay. So let's see what we've got to do to do this. Let's see. We've got, if we want to get the matrix xy. Let's think about what we have so far, or negative xy. We got x, y. We're going to multiply that by, let's call it A, B, C, D. And we're trying to get the value that multiplied together gives us the value negative x, y. That's what we're looking for here. Okay, so what is xy times all this stuff? So first of all, this would be, if we split this up, we'll get x A plus yc for the first entry, and then we will get, let's see, we'll get x for the second entry. We'll get xb yd plus yd, the second entry. Okay, so we want this to equal the same thing as this. We want these two things to equal each other, to the same answer. That's what we're looking for here. Okay, so we've got xa plus yc. We want xa plus yc to equal negative a. That's what we want. Or not negative a, now we want that to be equal to negative x. Negative x, and we want xb plus yd to equal just y. Okay, how can we do that? What values can we put in here? Well, if I want negative x, I don't want a y. So I don't want a y at all. If I don't want any y at all, I want to make sure c is 0. So I'll get rid of that y. So I'll make c 0. And then a, I want a negative x. So maybe if I make a negative 1, that'll do it. And then for let's see, for y, if I want to get y, then I want to make sure that x disappears. So I'll make b 0. And then for d, I'll make that 1 because that y times 1 is just y. So that'll do just fine. So that gives me exactly what I need. So a equals 1, a equals negative 1, b equals 0, c equals 0, and d equals 1. That'll do it, I think. I think it'll do just fine. So we'll plug it in. So our matrix then is negative 1, 0, 0, 1. And that will be our answer. So we want to plug in. We multiply it by negative 1, 0, 0, 1. That will give us exactly what we're looking for. And this is actually very, very similar to the identity matrix. If you know how identity matrices work, and you've tried multiplying a little bit with identity matrices, you'll realize this is not only almost exactly the same, but the only difference is that this first value, the x coordinate, the x spot, has become negative, which makes the only change is that x becomes negative. So that's the answer to that one. That's how you solve a problem like that. And so you've proven that if you multiply this by this matrix, you can, and you have your points structured as a matrix, you can create a reflection by doing that. So I guess it's a little bit of abstract math there to end it off. I really wish these problems stuck more to the practical side because this is extremely practical. This is used all the time in database mathematics. But I hope this is helpful. I hope this is actually a little bit fun. And in the next few lessons, we've done a lot of pretty powerful things so far, and really, really useful things so far, especially with helping compute important things for like people's wages, for example. But the next few lessons, we'll get more and more and deeper down the rabbit hole to do some of the more incredible and just insanely powerful things that matrices can do. And so I'm excited, and I'll see you there.